So this is the sixth video for EE114 module on power engineering, and here we will talk about rotating machines. So we will start with the basics. So first we will talk about windings in a rotating machine, right? So these carry the current in the rotating machine, and there are two windings called the armature winding and the field winding. What are their jobs? The job of the field winding is to produce a very high magnetic field, and then the job of the armature winding is to experience some force because of that magnetic field. So both carry the current, but basically the field windings current produces the magnetic field, and the armature's current feels the magnetic field and hence experiences a force. And in rotating machine, actually it experiences a net torque, not a net force. So then you can also segregate them based on a stator or rotor basis. So in any rotating machine, there are basically two components. One is the stationary component and one is the shaft, which is the rotating component. So there should be net movement between these two, and there should be something which causes a net torque production between these two. In an electrical machine, this is because of magnetic field interacting with the coils. So it is not necessary that the field has to be produced by the stator and the rotor has to experience the force. Sometimes the other way also can happen, that the rotor actually produces a very high magnetic field and it tries to apply a force on the stator, and by Newton's third law we know that it will apply an equal and opposite force. So now in AC synchronous machines, it's usually the rotor that has the field winding. So it is the rotor which produces the main magnetic field, and it is the stator which feels the magnetic field. Also in AC synchronous machines, usually what happens is we are using it as a generator. So what happens is the rotor produces the magnetic field, it creates some flux through the stator winding, and then as the rotor rotates, that flux changes through the stator winding, and hence in the stator winding some EMF is produced. Now most of the other machines have the field winding on the stator, like induction machines or DC machines. And here is a typical cross section of a machine, right? So here we have the stator, here we have the rotor, and it is important to observe both of them have slots. So what do these slots do? The job of these slots is two things. First of all, the depression in these slots that has to carry the windings, and the this is the region through which the current will flow basically. And this protrusion that these are called the peaks or sometimes the poles. What the job of these projections is that basically focusing the magnetic field through this. So what happens is that suppose the field winding is on the stator, so the currents are here, and then they produce a magnetic field which is then focused by this magnetic material sharply in this direction. Now both of these windings produce some MMF, right? And the interaction of these MMF is what produces torque. Now we'll talk about concentrated winding and distributed winding, right? So suppose you have some winding. Now don't concentrate on the three phases. Let's just talk about the red phase, right? So there is some winding here, some winding here. This is the rotor and this is the stator. So this will produce a square MMF wave. What do I mean by this line? What I mean is that suppose there is some current that is flowing through here, some current that is flowing through here, right? So what will happen is most of the MMF will basically flow perpendicular to this coil, right? It will flow like this and in this direction. So what that will basically do is there will be the whole air gap that exists here. We are assuming that there is no MMF drop in the whole of the magnetic material. So what happens is there is some MMF drop in here, there is some MMF drop in here. In concentrating winding, what happens is these windings are not distributed over space. This is very finely pinpointed. So there is current going in here and coming out of here, right? So what happens is the MMF produced will be symmetric on both sides, and it will be almost linearly set out, because what will happen is if you take any loop that encompasses this current, we will have h dot dl equal to ni, since ni is same across all loops and the air gap also has the same thickness across all the points. What will happen is the MMF will look like a rectangular wave. It will go up and down, and the sudden upthrusts will have the uh, amplitude of ni. So up and down, ni over 2, ni over 2 will come, and then hence the upshot that occurs at the crossing of each coil would be of amplitude ni. Now Square MMF is not what you want to produce current or to produce torque. You need a sinusoidal wave. So you use distributed winding. So what you do is, instead of being concentrated at one point, distribute the current, and this makes it much more smoother. So it first goes slowly up and then slowly down, and that's what is a sinusoidal wave. So you have to distribute the winding such that it looks like a sinusoidal wave. And you could also use short pitching. Now short pitching means that, suppose some wire goes in here and instead of coming out here, it starts coming out here. So what this does is, it actually shortens the amount of harmonics you have, and if you have lesser harmonics, then that means that the fundamental has more components, so it looks more sinusoidal. Now this introduced something called the winding factor. What the winding factor means is that the torque that you are getting from the concentrated winding, that will get reduced, but the torque won't be so edgy like it was before. So the net torque will be a little less, but it will be much more smooth. Now what is the MMF wave actually that we have been talking about yet? So suppose that the distributing winding produces a sinusoidal MMF distribution in that whole air gap, right? So the MMF distribution in that air gap is sinusoidal. Now you pass sinusoidal current through that winding. So what will happen is, it will look something like this now, because it was already of the form sine kx along that air gap. Now it is also sine omega t, because now you are varying the current also sinusoidally. So if you remember, this looks a lot like a standing wave. So basically in that air gap you have set up a standing wave, and we know that a standing wave is actually the superposition of two waves traveling in opposite directions, right? So now try adding three standing waves that are set off 120 degrees both in time and in k, I mean in space. So basically you have three windings, and each one of them has 120 degrees phase difference both in space and in time. Then you try to resolve them into the components that follow clockwise and anti-clockwise, and what the math will tell you is that, suppose we add them such that the ones leading in position also lead in time. So you will see that the clockwise components will all add, but the anti-clockwise components will actually cancel each other out. So what you will get is that you will get a moving wave. That MMF wave will now start moving clockwise in that air gap. So now this is a rotating MMF wave, and this wave has some rotational speed. This is called the synchronous speed of the MMF wave, and it is important to note that the synchronous speed of the MMF wave is same as the frequency of the current that was producing it. So you had been producing some current here, right? The omega, this omega and the omega of this wave, they are the same. So now both rotor and stator possess these MMF waves, and now they will have some feature of locking. These MMF waves will try to lock with each other, and that is what will cause the torque production. So before we go on to that part, we must first understand something called poles. Now the MMF wave that we have created, we have been talking about it going up and down, and once it goes once up and then once down, it simply does one whole transaction in that air gap. It has covered 360 degrees. But we could produce an MMF wave that has more than one loop in the same 360 degrees, right? It could have two wavelengths, it could have three wavelengths. So the number of half wavelengths that this MMF wave has, is called the number of poles. The number of poles is basically the number of windings that you will require to produce that MMF wave. Because to produce that two pole winding, you needed that two pole MMF wave, you needed two windings. One that was making all the current flow in one direction, one that was making all the MMF flow in the other direction. Then you saw that one of those components cancelled, one of them got added. So that's why we could see that there was a net MMF wave traveling. So if you have more than two poles, you are going to need more than two windings. Now suppose you have a 4-pole motors, right? So in this 4-pole stator winding, you can see that there are actually 4 sets of windings. 2 that go in and 2 that come out of the plane. So these produce magnetic fields that look like this. So now you can understand why it's called pole, because according to the rotor, this will look like some magnetic pole, this will look like a magnetic pole, this will look like a magnetic pole, this will look like a magnetic pole. Why? Because all the field is going in one direction here. So suppose this looks like north, then this will look like south, this will look like north, this will look like south. So there are 4 poles the rotor is seeing, so it's a 4-pole winding. Similarly here it will see 8 poles, so this is an 8-pole winding. So now just take one pair of poles right? You take one pair of poles and you just define that as 360 degrees of something, not of the mechanical angle, but it is 360 degrees of something. Now that something is called an electrical angle. So obviously, since P over 2 times 360 degrees of the electrical angle forms 360 degrees of the mechanical angle, that is what forms the ratio of electrical angle and mechanical angle, the number of pairs of poles. Now you can analyze each pair of poles individually, and what will happen in the rest of the pair poles will simply be the repetition of this. Now there is a famous formula called 120 F by P. So what this is that if you are given the frequency of the current or the MMF wave that is flowing, you first need to convert that into the mechanical frequency. So we know that the factor is P by 2. So 2F by P in Hertz is the frequency of the rotor. But if we want it in RPM, since Hertz is RPS, we need to multiply that by 60. So 60 into 2F by P is 120 F by P, and this is the RPM of the rotor mechanically. So this connects basically the mechanical frequency and the electrical frequency. In DC machines, there are projections in the stator. See, this part where the magnetic field is coming out, in DC machine this will be projected outward so that the magnetic material can very heavily focus that magnetic field right in that direction. So in DC machines, the stator has such projections to enhance the poles. In AC machines, the rotor has such projections to enhance the poles. Instead of the stator coming inwards, the rotor comes outwards. So that's called a salient pole. It is possible that in AC machines, neither of them have these weird projections. So that's called a round rotor AC motor. Now, how does torque produce eventually? How does torque production actually happen? So what happens is, let the stator produce some MMF wave Fs, let the rotor produce some MMF wave Fr, right? These are the amplitudes, and let them have the same frequency, which means let them have the same speed, because the frequency, the electrical frequency was the same as the synchronous speed, right? Now, but let them have some arbitrary phase difference, the two waves that we have. So we have two waves, same frequency, but they have a phase difference phi. So now the energy that they will possess is proportional to the cos of the angle between them. This cos phi, it is proportional to that. So if you try to find out the torque using that formula, what you will get is that torque will be proportional to Fs Fr sine phi. So it will be proportional to the strength of the MMF waves and also of the sine of the angle between them, right? So if the angle is 0 degrees, the alignment torque will be 0, and hence there will be no torque production. But if they are out of phase, they're exactly out of phase by 90 degrees, then the most amount of torque that is possible for Fs and Fr will be produced. Now, if they are not of the same frequency, because we have assumed that they are of the same frequency, but if they are not, what will happen is one of them will go a bit faster and then it will catch up and come from behind. So now the alignment torque was first in front direction, then in back direction. So the torque net averages out to 0. So you need them to have the same speed to have some constant torque production, and then that constant torque will be given by this formula. It will be proportional to this. It will not be equal to this. And suppose you have such a situation, right? So this is a concentrated winding, this is a concentrated winding, and this is a salient pole, because the rotor has such projections to enhance the poles, right? So here Fs and Fr are completely aligned. There is no torque production here, right? But if they are a bit off, this south will try to pull this north will try to pull this south, the rotor will try to rotate a bit, and as soon as it tries to rotate a bit, it will create some torque in the shaft that will be proportional to the sine delta term. Thank you. This is the end of the 6th video.